Good thing for a Monday. Keep me awake. All right, there, Chemistry 3101. Today we're going to talk about Chapter 6, which is chemical reactivity and mechanisms. I'd say that the first half of the chapter is the chemical reactivity portion, and then the second half of the chapter is kind of the mechanisms portion. So let's start by talking about enthalpy. I know you guys all would have covered the concept of enthalpy in General Chemistry 1 and in General Chemistry 2. You use an H to represent enthalpy. And then sometimes we use a Q, okay? So again, both variables are acceptable. So it says here that enthalpy is the heat energy exchange between the reaction and its surroundings and at constant pressure. So I added that in there for my students as a reminder that when we do most reactions in organic chemistry, the vast majority of them are done at constant pressure. That means that the reaction flask is open to the environment somehow. Okay, they're usually not in some kind of sealed vessel. So again, let's review that. It says enthalpy, delta H or Q, is the heat energy exchange between the reaction and its surroundings. So some reactions release heat to their surroundings and some reactions absorb heat from the surroundings. And if the words exothermic and endothermic are starting to ring around in your head, you're right, okay? We're going to get into that in just a little bit. But let's talk about bonds, okay? You guys know all about carbon-carbon bonds, carbon-oxygen bonds, carbon-hydrogen bonds. But let's think about a bond for a second. If you have a bond between two atoms, let's say you have a bond between two hydrogen atoms to make an H2 molecule, okay? Why does bonding occur? Well, we covered this back in Chapter 1. The whole rationale behind bonding is that it says here that electrons will achieve a lower energy state when they occupy a bonding molecular orbital. So if you need to go back to Chapter 1 and review that, do that. But again, let's review. It says the electrons achieve a lower energy state when they occupy a bonding molecular orbital. So what's the conclusion that we can take from that? You know, students like rules in science where there's no exception to those rules. And here's one, and you want to highlight this one, is that breaking a bond requires the input of energy. Okay, my friends, anytime you break a bond, okay, it always requires the input of energy. If you break the bond between these two hydrogen atoms, it requires the input of energy. If you break a bond between a hydrogen and an oxygen or two carbons, it always requires energy to break bonds. And so what does that tell you? It tells you that energy is going to be released when you form bonds. So let's think about that. If it takes energy to break a bond, that means when you make a bond, energy is going to be released. And you see that here. Okay, we have the two unpaired electrons, and when they go into a bonding molecular orbital, it's lower in energy. And based off of the laws of thermodynamics, that energy can't be created or destroyed. Energy would have to be released overall. Now, when it comes to bonds breaking, okay, I think you all follow me on, yep, okay, breaking a bond requires energy. Good. Well, it turns out that you guys all know that if I draw any bond, so let's go back to that H2 bond. Can anybody tell me, and it's not a trick question, how many electrons are there in a bond, whether it's a sigma bond or a pi bond? We always have the same number of electrons in a bond. Thanks. Exactly. It's 2 electrons, okay? So when we break a bond, whether it's a sigma bond or a pi bond, doesn't matter. There's 2 ways that we can break the bond. We can break them homolytically, okay, so homolytically, or we can break them heterolytically. So homolytically is shown at the top, or homolytic bond cleavage, okay? And you recognize the fishhook arrows, and you're probably thinking, well, you said we weren't going to cover those until Chapter 10. We don't. But I did tell you that a fishhook arrow, these arrows here, they represent the flow of just 1 electron. So this is 1 electron moving, and this is 1 electron moving. You know that because the arrow just has a single barb on the end, okay, if you didn't pick up on that. So in the case of homolytic bond cleavage, we end up with 2 atoms here that have an unpaired electron. And remember, when we have an unpaired electron, we call that a radical. So unpaired electron. So that's homolytic bond cleavage. Everybody gets 1 electron, and you end up with a pair of radicals. And then heterolytic bond cleavage, we're going to see that also towards the end of this chapter. That's when one atom takes both electrons and becomes an anion, and the other one loses its electron, so it becomes a cation. So you end up with a pair of anions. But when we're talking about calculating delta H of a reaction, and this is something that you should remember from General Chemistry 1 and 2, you would have calculated delta H for a reaction. So RXN is just my shorthand form for reaction. For those, when we're calculating the delta H of a reaction in an organic chemistry, we actually use bond association energies that are the result of homolytic bond cleavage, okay? So when I give you a table, or you see a table of bond dissociation energies, which is nothing more than the delta H, or the amount of energy required to break a certain bond, that is always measured using homolytic bond cleavage. So if you're wondering, could you give me some ideas of some numbers? Sure, here you go. This is not an exhaustive table. This is part of the table that is found in your textbook. It's table 6.1. I told you, you do not have to memorize any of these. If you have a great memory, knock yourself out if it's something that you want to do. But you see that the amount of energy required to break a hydrogen-hydrogen bond, so an H2 molecule, to break it apart, is 104 kilocalories per mole. You guys know that there's 4.184 joules in a calorie, and so it takes, you know, roughly 4 times as much in terms of kilojoules per mole. But you can see we have all these different bond dissociation energies here. Let's take a look at some other ones. What if you have a methane molecule, CH4, simplest organic molecule in the universe, right? The bond dissociation energy for that carbon-hydrogen bond is 435 kilojoules per mole as well. But look at this. The carbon-hydrogen bond in ethane is 410 kilojoules per mole. So you see it's weaker, okay? Then we go to the halo acid. So you have HF, HCl, HBr, HI. You can see their bond dissociation energies are there. The hydrogen-oxygen bond dissociation energy in water, et cetera, et cetera. We have a whole plethora of different types of carbon-carbon bonds. Bonds between carbon and halogens are in here. The halogens, and obviously they're not all in here. This is, again, not an exhaustive table. So what, if you're wondering why are you showing me all these numbers, the reason I'm showing you these is because you will probably be asked to calculate the delta H of a reaction in quiz 6, maybe on the final exam. And so I'll give you bond dissociation energies, and you'll have to know how to use those. Okay, that's really all there is to it. And again, you don't need to memorize these. If you need them, they will be given to you. Okay, so here's a more exhaustive table. This actually, I think, comes from another textbook, but there are some trends in here that I wanted to show you. So nothing major, but I'd say like some of the important trends would be if you look at single bonds versus multiple bonds. So if you compare a carbon-carbon single bond versus a carbon-carbon double bond versus a carbon-carbon triple bond, what do you see? You see that as you increase the number of bonds, you see the bond dissociation energy goes up, right? It's going up from, darn it, it's going up from, where was I? From 347, okay, up to 614, and then it skyrockets all the way up to 839, okay? And then if you look at the bond lengths, what do you notice? You notice as you add more bonds, you go from 154 down to 134, down to 121. So we see that as the bond strength increases, what happens to the bond length? It gets shorter and shorter. And if you're thinking, didn't we already cover this earlier on? Yes, we did. However, now we're just kind of looking at some numbers in this table of bond dissociation energies. Anyhow, so with that in mind, it says here, most reactions involve the breaking and forming of bonds. Well, that's for sure, okay? So if we look at a simple reaction like the combustion of methane, so methane is a gas. If you combine it with oxygen, right, it burns, okay? So it releases carbon dioxide, which is a gas, plus water, vapor, okay? And if we balance this reaction, we have 1 and 1 for our carbon, we have 4, we need a 2 here, and then we have a total of 4 here, so we need a 2 here. So there's our balanced equation. But you can see, if you're wondering, what's your point, Mr. Dion, why are you writing down this reaction? My point is this. If you take a look at the reactants, let's just look at the methane, CH4, okay? In CH4, there are 4 carbon-hydrogen bonds, okay? Look at the products, carbon dioxide and water. Are there any bonds between carbon and hydrogen in here? No. Therefore, all the bonds between the carbons and the hydrogen, they were all broken, okay? And we formed bonds between carbon and oxygen, et cetera, et cetera. And so the point is, in order for this reaction to occur, we had to break these bonds. So you could put here bonds were broken, okay? And then when we formed the products, bonds were formed. And so how would we think about that in terms of energy? It means you have to put energy in to break those bonds. And then when you form the bonds, energy is released. So let's put a name to reactions when energy is released versus when energy is absorbed. So an exothermic reaction, and again, I know you all know this, is a reaction where the energy released by the bonds formed exceeds the energy needed to break the bonds. So that means your products are more stable than your reactants. And another way you could think about it is you could say heat is released, released by reaction. Or you could also say the delta H is negative, right? Delta H is negative for an exothermic reaction. And then for an endothermic reaction, it's just going to be the opposite. The energy, required to break the bonds exceeds the stability of the bonds that are formed in your products. And so we'd say here, heat is absorbed by reaction. Okay, or you could say your delta H is positive. Delta H is positive, like that. Now, if you're looking at this and saying, hey, I remember this, and didn't they have like these reaction coordinate diagrams in General Chemistry 1? I'd say, yeah, absolutely, and here they are. Okay, so these are just reaction coordinate diagrams for exothermic versus endothermic reactions. Everything's color-coded here. All the red is exothermic, the blue is endothermic. And so if we take a look at the formula that you would have used for the delta H of a reaction in General Chemistry 1, I'll scribble it down here for you. So let me see, I've got maybe enough room here. So we'll say if you took General Chemistry 1 and General Chemistry 2 here at UCCS, it's Chemistry 1401, and you might have seen this in 1411 as well. So it's the delta H naught, so this is a standard state of your reaction, is going to be equal to the sum of the stoichiometric coefficients multiplied by the change heat of formation of products, okay, minus the sum of the stoichiometric coefficients multiplied by the change in the heat of formation of the reactants, okay? And that's the formula that you would have seen. Give me a thumbs up if you even like have a tiny memory of this formula. You would have used it in General Chemistry 1 and probably in General Chemistry 2 as well, okay? Good. Okay, now if the formula is intimidating to you, all you really have to remember is that the delta H of reaction is the delta H of the products minus the delta H of the reactants. Okay, this was the way you did it in General Chemistry 1. I'll just give you a heads up. It's not how we're going to do it in this class. However, it does help us understand why the delta H for an exothermic reaction is negative. So let's think about this. If it's products minus reactants, you see your products have a low H and your reactants or your starting materials have a high H. If we take a low number and we subtract a high number, so let's say you take a low number like 1, subtract a high number like 2, what do you get? You get a negative number. So that explains why the delta H for an exothermic reaction, where the products are more stable than the reactants, is negative according to the formula. So we see here that energy is released as heat, which is a kinetic energy. The delta H is negative, and the temperature of your surroundings in an exothermic reaction is going to increase. If we look at the endothermic side, again, same rationale. If it's products minus reactants, you take a big number, right? A high number, subtract a low number. Let's say you take a big number, like 2, you subtract a smaller number like 1. What do you get? You get a positive number. So that tells you why the delta H is going to be positive in this case. So in this case, the products are higher in energy. Energy is consumed. The delta H is positive, and the temperature of the surroundings is going to be consumed. And this is why in endothermic reactions, if you do a reaction in, let's say, a test tube and it's endothermic, the test tube will feel cold because it absorbs the heat from your hand. All right. Anyhow, so what we are going to be doing in Chemistry 3101 is going to be something different. Okay. So I'm going to scribble it over here, and I'm going to copy and paste it into the next slide as well. So in Chemistry 3101, we're going to calculate the delta H of our reaction, but we're not going to do it the same way. We're going to say delta H of our reaction, okay, is going to be equal to the bond dissociation energies of the reactants. So bond dissociation energies of the reactants minus the bond dissociation energy of the products. Okay, now we're going to talk about entropy and Gibbs free energy later on today. But if you remember, in General Chemistry 1 and 2, all of those formulas, they were always products minus reactants, like I have on the top, okay? In Chemistry 3101, we're not going to do it that way. We're going to use bond dissociation energies, and it's going to be reactants minus products. This is the only formula in chemistry that you're ever going to see that's going to be reactants minus products. It's when we use bond dissociation energies. Let's think about it. Why would it be switched? The reason why is because the bond dissociation energies of the reactants, you plug them into the formula the way they're written because energy has to go in, right? The bond dissociation energy values that we saw in this table, they're positive numbers. So you plug them in, and that tells you how much energy it takes to break the bonds. But then when the products are formed, you take their bond dissociation energies, but you put a negative sign in front of it. So you subtract that energy, okay? Now, if you have to sit at home and think about this for a little while to understand it, that's totally fine. And maybe when you see it used in a problem, it will help it crystallize in your mind. So let's take a look at a problem where you'd be asked to use the formula that I just showed you. So it says here, using the data from table 6.1, predict the sign and magnitude of delta H naught for this reaction. Okay, so we're asked to calculate delta H naught. Identify whether the reaction is endothermic or exothermic. So if delta H is positive, it's endothermic. If delta H is negative, it's exothermic. Cool? So let's write down the formula again. So it's going to be the delta H naught of our reaction is going to be equal to the bond association energies of the reactants minus the bond association energies of the products. Now, since I'm teaching the class, I've gone ahead and I've looked up all the bond association energies from the table. You can go in there and find them. It's not that difficult. But could anybody name this molecule that I'm putting in the blue circle here? We'll do a little review of chapter 4 for a split second here. Could anybody name that molecule? It's got 3 carbons in a row. Yeah, thanks, Rubio. Exactly, it's propane, yeah. So you can see that in propane, right, there's bonds between carbon and hydrogen in here, and carbon, but the only bond that's being broken is this one here between this carbon and hydrogen. So that bond is being broken. And I went up and looked up that bond association energy. It's 397 kilojoules per mole for this bond. And the other bond that's going to be broken is going to be the bond between our 2 bromines, okay, the bromine bond. And I went and looked that one up, and it is 193. So we'll put here 193 kilojoules per mole, right? And if you're looking at the propane and going, well, what about, this bond? Okay, well, that bond is not being broken, right? You can see that bond is perfectly intact, as are all the other bonds, okay? So those are the 2 bonds that are broken. The bonds that are formed, I'll write them down in red. The first one is this one here between the carbon and the bromine, and I've gone ahead and looked that up, and that's 285 kilojoules per mole. And then the bond between HBr, I looked that one up too. It is, what was it? It's 368. So 368 kilojoules per mole. Okay, so now that we have the bond association energies of the bonds that are broken, right? These are the bonds that are broken over here. And then the bonds that are formed, all we have to do is plug the numbers into the formula. So let's give it a shot here. So we're going to say the delta H naught of our reaction is going to be equal to the bond association energy of the reactant. So we have 397 plus 193. I'll put kilojoules per mole all at the end. So I'll just put this in a bracket here. Subtract 285 plus 368. And I'll put all that in brackets, kilojoules per mole, like that. And then we get the delta H naught of our reaction. When you plug all these numbers into your calculator, you end up with negative 63. So I did this one ahead of time, negative 63 kilojoules per mole. So is this reaction endothermic or exothermic? Can anybody tell me? It's not a trick question. Anybody? Is this endothermic or exothermic? Yeah, thanks. You guys, great. Awesome. Everybody nailed it. So since delta H is negative, therefore exothermic. You know something about endothermic and exothermic reactions? Okay, something about endothermic and exothermic. In our everyday lives, when we think of reactions that are spontaneous in our everyday lives, right? Think about combustion, right? That's one of the most common reactions we see in our everyday lives. That is a spontaneous reaction, right? If you burn gasoline, right, it just takes a spark and then it will burn, right? If you make a campfire, that will burn, right? If you burn natural gas at home to heat your house or heat your water like I do, those are spontaneous reactions, right? We burn fuel in our bodies, okay? That's a spontaneous reaction. And it turns out that when it comes to whether a reaction will be spontaneous or not. So let's think about this. Spontaneous. And spontaneous doesn't mean it's going to get up and do it itself. Okay, it's not magic. It just means once the reaction starts, it's going to keep going. It's not going to stop. Okay, a spontaneous reaction in our everyday lives, the vast majority of them are exothermic. Okay, I'd be the first guy to admit that. Yes, the vast majority of spontaneous reactions in our everyday life, they are exothermic. However, you should remember, and if you don't, I'll review it with you right now, from General Chemistry 1 and 2, that enthalpy is not the ultimate deciding factor as to whether a reaction will be spontaneous or not, okay? The ultimate deciding factor as to whether a reaction is going to be spontaneous is actually entropy, okay? And if you don't remember entropy, let's review it. So entropy is S, so changes in entropy would be delta S. And it says here that yes, exothermic and endothermic reactions, they can both happen spontaneously. There's no doubt about that. It says here that enthalpy and entropy, however, have to both be considered when you're predicting whether a reaction will occur. So when it says will occur, that just means, is it spontaneous, yes or no? Spontaneous, okay, or not. Okay, that's what that means, okay? So recall that entropy, if you don't remember entropy, I always think of a messy bedroom, you know? You clean your bedroom up and it's all nice and tidy and everything, and then it takes like no energy. It just spontaneously becomes disorganized, right? Or my car, I clean it up, then spontaneously somehow there's, you know, napkins all over the place and my kids throw goldfish crackers or whatever. It takes no energy to do that. So entropy is molecular disorder or randomness or freedom. It's really nothing more than probability. If you read the chapter before coming to class today, there's a whole section in there about coin flipping where he talks about, you know, you flip 2 coins, you flip 4 coins, you flip 1,000 coins, et cetera, et cetera. And you can go through that. I'm not going to use that treatment. I find it's not really necessary. But again, entropy is nothing more than disorder, randomness, or freedom. And so when we have a process that involves an increase in entropy, so I'll highlight this here, an increase in entropy. That's not a highlighter. That's a highlighter. If it involves an increase in entropy, you say the delta S for the reaction is positive, okay? So there's actually 2 dominant factors that affect entropy in organic chemistry. So I actually have some good news for you. I find that students usually actually say that the way that we treat entropy in Chemistry 3101, which is the way it is on this slide, is actually less complex than their general chemistry days, because in general chemistry, they ask you to look up entropy values in a table sometimes. We don't do that in this class, or we don't have to. There's 2 ways that we see increases in entropy in Chemistry 3101. Okay, so in this class and in chemistry, I'll put here 3101 and 3111, there's 2 things that can have increase, or ways we can see increases in entropy in organic chemistry. The first one is if you have 1 mole of something and you end up with 2 or more moles of something. So you start it with 1 molecule and then it breaks apart into 2 molecules, or an atom and a molecule, whatever. Okay, that would involve an increase in entropy. Okay, so literally one thing becomes 2 or more things. And you're like, well, that makes sense because there's only one way to organize one thing. But if I have 2 things, I can organize them more than one way. Okay, and the second thing is if you have a cyclic compound and you break it apart, okay, so that it has more freedom of movement, then that would be an increase in entropy as well. So for both of these systems, delta S would be a positive number here, and your delta S would be a positive number here. Give me a thumbs up if you're with me on that. 1 becomes 2 or more, that's an increase in entropy. Or if you go from something that's cyclic and kind of bound, or not kind of, it is bound together tightly, and then it breaks apart to have more freedom of movement, then that would be a positive delta S as well. Okay, if you're not 100% sure, let's take a look at a problem. Okay, it just says here in 6.3, for each of these processes, there's 2 reactions here. Tell me whether the sign of delta S is going to be positive or negative. Is there going to be an increase in entropy or a decrease? Okay, so let's take a look at A. Okay, in A, I'm starting it with 2 molecules. 2 molecules, and then I end up with 1 molecule. This reaction has a name. It's named after 2 scientists. This is called the Diels-Alder reaction. We don't cover it in this class, but we cover it in organic chemistry too. But you see I'm going from 2 molecules to 1 molecule. So how about my delta S here? Would my delta S be positive or negative in this case? It's going to be negative. Exactly. We're decreasing the entropy. Good. And what about the second one? So the second one, this is the start of what's called an SN1 reaction. Anyhow, and we'll cover that later on as well. But here we're going from one molecule. So one, or yeah, I'll just put here one molecule to two ions. We end up with a carbocation and a bromide ion. So thanks, you guys. So my delta S here is positive. Awesome. Awesome. There you go. So give me a thumbs up. Everybody with me on the entropy idea of, you know, as long as it becomes more disordered, entropy is increasing. If it becomes less disordered, entropy is decreasing. There you go. Good. Okay. So let's concentrate on entropy for a couple more minutes. So I told you that it's not delta H that is the ultimate deciding factor as to whether a reaction is spontaneous or not. I told you that it's actually delta S. However, when we're considering the delta S for a reaction as to whether the reaction is going to be spontaneous or not, we have to consider the delta S of both the system and the surroundings. So the system is just another word for our reaction vessel, and then the surroundings is the area surrounding our reaction vessel. So let's take a look here. So recall the spontaneity of a process relies on the total entropy. So total entropy is the entropy of the system, which again is nothing more than a fancy way of saying your reaction. And then the surroundings is just the area around your reaction. Now, if I want to measure the delta S for a system, I don't like to say that anything is easy in chemistry, but it's very doable, because for your reaction, you can just go up and look values up in a table, okay, for your system. However, the delta S of your surroundings, I mean, there's no direct way to do that, okay? There's no direct, easy way to calculate this. However, and this is beyond the scope of our class, we're not going to go into the details of this formula right here, but it's actually been determined that the delta S of the surroundings is equal to the negative of the delta H of the system divided by the temperature in Kelvin. So what's the consequence of this? We have delta H of the system. Can we calculate the delta H of the system? Yes, we can look up those values in a table as well. So now we can plug this into the formula down here, and we say the delta S of the total delta S. So determining whether the reaction is spontaneous or not, this number right here is going to be equal to a calculation where we only use values that we can get from a table. So that's great. So now what we do, if you're looking at this formula at the bottom and saying, what the heck is that? Okay, well, what you might or might not remember is that what you do with this formula is you take the whole thing and you multiply it by negative T. Okay, we're going to take that entire formula and multiply it by negative T. And when you do that, what do you get? You get negative T times the total entropy is equal to the delta H of the system minus T delta S of the system. So what is this negative T times delta S? Well, again, if you don't remember, here's the definition. It turns out that negative T times delta S is delta G. Well, let's think about this. If when delta S is positive, that's spontaneous. So if you have a positive number, if you have a positive number, your delta S multiplied by negative T, that means that when delta G is negative, you get a spontaneous reaction. Okay, when delta G is negative, it means your reaction is going to be spontaneous. And conversely, when your delta S is negative, when the reaction is non-spontaneous, you take a negative times a negative, you get a positive. So it might be a little bit counterintuitive. I don't know. It depends on the person, I guess. But the bottom line is what I have highlighted in yellow. If your delta G value is negative, your reaction is going to happen. Good, you're good to go. The reaction will work. If the delta G is positive, forget it. It's not going to happen, okay? It's not going to work. You might get a little bit of products, but it's mostly going to be reactants, okay? So there you go. So here's the formula. And what's cool about delta G is, if you've never been told this before, and if you ever had me as an instructor, I always make a point of saying this, is that Gibbs, you can look him up, is Willard Gibbs. Willard Gibbs was an American scientist, and if you think about, you know, Marie Curie and Albert Einstein and all these people that we talk about, they're all Europeans, but Gibbs was born in the USA and died in the USA. And don't pass Gibbs off, because he was friends with Albert Einstein, and Albert Einstein said, I can't even believe how smart this guy is. He makes me, he actually said, like, Gibbs is actually very intimidating. He's so brilliant. So anyhow, kind of a cool bit of history for you there. So if you don't remember, let's review a little bit more about delta G. So you had exothermic and endothermic. Those are terms we use a lot as chemists. Endergonic and exergonic, not as much, but they are important and you need to know what they are. So when your process has a negative delta G, meaning it's going to be spontaneous, the word we use for that is an exergonic process. And when you have a reaction where your delta G is positive, so if delta G is positive, we call that an endergonic process. And you can see the reaction coordinate diagram here. In an exergonic process, the products have less free energy than the reactants, and then it's the converse for an endergonic reaction. So endergonic and exergonic reactions. So there you go. So a little bit about Gibbs free energy. Everybody give me a thumbs up if you're with me so far. So we've kind of covered up till now, like if you're like, where are we? Okay, we've covered delta H, then we covered delta S, then we covered delta G. And if you need a little more help, so in delta H, we covered endothermic and exothermic reactions. And we said, well, most spontaneous reactions are exothermic, but not all. There are plenty of endothermic reactions that are spontaneous. And then we said, well, it actually turns out that what determines whether a reaction is spontaneous or not is actually delta S. And then we said, well, delta S, you know, we don't have a way of determining delta S of the surroundings. So then we said, well, actually, it's equal to the negative delta H of the system divided by temperature. And then Gibbs came up with this formula here. So he derived that last formula. And so we say if your delta G is negative, you have an exergonic reaction, your reaction is spontaneous. If your delta G is positive, you have an endergonic reaction and your reaction is non-spontaneous. So that's kind of a Sparks Notes version of the first three sections of the chapter. But if you think about, if any of you took General Chemistry 2, so Chemistry 1411, I know that not all of you, but I know a few of you took that class this spring. Okay, so it's probably fresh in your mind. If you think, and even if you took it, let's say a few semesters ago, if you think about that class, General Chemistry 2, I think that almost half of General Chemistry 2 is talking about equilibria. It's equilibria this and equilibria that. If you think about all the chapters about acids and bases, or the chapter about when you did Ka and Kb, and then you studied K equilibrium, then you did Ksp. Who remembers Ksp, right? All those things, okay, that you would have covered in General Chemistry 2. So Ka, Kb, K equilibrium, Ksp, all that stuff, okay? That is all equilibria, and that's what we're going to talk about now. So if you're wondering, like, when was that going to show up in this class? Here it is, okay? So, and if you're thinking about, you know, delta G is equal to the negative ln of RTK, right? So we'll talk about that formula as well. So let's take a look here. It says, consider an exergonic reaction. We said exergonic process is one where your delta G is negative. Now, this is something that's kind of new. Like in General Chemistry 1, we just gave you reactants, give you products. You know, that's it, okay? But in General Chemistry 2, you learn that is every single molecule of A and B going to be converted into products? The answer is, when you have a reaction like this, the answer is no. Not everything is going to be converted into products, because you know that this arrow represents equilibrium, okay? Remember that this arrow, if you have a double-headed arrow like this, this is resonance, okay? But if you have this kind of arrow where you have one on the top, one on the bottom, that is an equilibrium arrow. And you guys know that if you mix A and B, it's not all going to give you C and D. Sometimes it could, okay? But many times we don't get only products. We get a mixture of reactants and products, and we say that an equilibrium is reached. Now, this actually happens to show an exergonic reaction where it is mostly products. So what it means by a spontaneous process, okay? A spontaneous process, its true meaning is nothing more than this. There's going to be more products than reactants, okay? That's a spontaneous process. So even if it's just 60% products and 40% reactants, I wouldn't say that's a great reaction, okay? It's not my favorite kind of thing, but technically it would be considered spontaneous. Now, what do we know about this value of delta G? We know the bigger this number is. So if the delta G is, let's say, a gigantic number, right? You have a huge gap between the free energy of your reactants and products. The bigger the gap, or the bigger the magnitude of delta G, then the greater the concentration of your product. So I guess I should say, the more negative your delta G value is, the more products you have, okay, and the less reactants that you have. So Why doesn't an exergonic process give you 100% reactant, or 100% products rather? The reason why is because as you start out, so here's the starting point of your reaction is right here. All you have is A and B, but then as the reaction progresses and you make more C and D, so this is just C and D, this is A and B, right? Eventually you make more C and D, and then the C and D molecules start colliding with each other and they start reacting and they give you the reactants again. And then at some point you get to this equilibrium where the rate of the forward reaction is equal to the rate of the reverse reaction. However, in this case, you can see that even though the rate of the forward and the rate of the reverse reaction are equal, we end up with more products because you can see it's closer. If this is the midpoint here, you can see you're closer to the products than you are to the reactants, right? So this is at this minimum value of delta G for this specific reaction. So if you calculate the K equilibrium, so the equilibrium constant, and again, this is something that you would have seen at UCCS in chemistry 1411. How do we calculate K equilibrium? We say that K equilibrium is equal to the concentration of our products divided by the concentration of our reactants. So what does that mean? It means if the reaction is spontaneous, we're going to have more products than reactants. So what does that mean? It means if your reaction is spontaneous, so we'll say here spontaneous, okay, that means your K equilibrium is going to be a big number. It's going to be greater than 1, okay? Whereas if your reaction is non-spontaneous, that means it's going to be mostly reactants, and in that case, your K equilibrium would be less than 1, right? If this number is big and this number is small, your K equilibrium is going to be greater than 1, right? That's the way equilibrium works. So now, if you plug those numbers into the formula, if you take the ln, so if you take the natural logarithm of a number greater than 1, then you end up with a positive number. So you take all of this, which is positive, and you multiply by a negative sign, you get a negative number. So that explains why when your K equilibrium is greater than 1, you end up with a delta G that is negative, right? Spontaneous reaction. However, if you take the natural logarithm, you can try it. Take the natural log of 0.5. You're going to get a negative number. You take a negative multiplied by a negative, you get a positive. So that explains why when you have a non-spontaneous reaction, K equilibrium is going to be less than 1. And in that case, your delta G is going to be positive, like that. So we see here that K equilibrium, delta G, delta H, delta S, these are all what? These are all thermodynamic terms. They only describe the relative stability of products and reactants, but they don't cover the rate. Okay, they don't cover the rate at which they're formed. And this is another subject that you would have covered in chemistry 1411 when you covered rate laws. Okay, so if you remember, rate is equal to little k multiplied by the concentration of your reactants to some exponent, right? And you had to determine those exponents sometimes by using the method of initial rates. Okay, that's going to come up in this chapter as well. But before we get to that, let's take a look at a summary. Okay, so this is kind of a summary of the section on equilibrium. So summary of 6.4 is this: if your delta G is negative, you got mostly products. Your K equilibrium is going to be greater than 1. If your delta G is positive, the reaction is non-spontaneous, it's mostly reactants, and your K equilibrium is going to be less than 1. In order for the reaction to be something useful, okay, that's not just going to waste your time, it's going to give you mostly products, your products are going to have to dominate over the reactants, and your delta G is going to have to be negative, which means your K is going to have to be greater than 1. If you're sitting there listening to me and going, isn't this just kind of rehashing what you said? Exactly. It's repeating it, okay? But it's just telling you that, yes, you have to have a negative delta G. Otherwise, the reaction isn't worth doing. You're wasting your time. And I'm not going to test you on this or anything, but I'll show you a table. It's right here, okay? Where a little, so what is it? Table 6.2. Let's just scribble this down here. This is table 6.2. It says here, a small difference in delta G, free energy, can have a significant impact on the ratio of products and reactants. So check this out. Even if you go from a delta G of 0 to a delta G of -6, you go from 50% to 90%. Now, if you're like, well, how do I know that's a big or a small change? You don't really, because you're kind of learning the subject, you know, when you're in this class. Okay, I don't expect you to be experts on thermodynamic values. But the bottom line is you can take my word for it, that it's just a small change in delta G makes a huge difference in the amount of products that you get here. And you can see that I quantified it here. 6 kilojoules per mole results in about 10 times change in the equilibrium constant. You don't have to memorize this or whatever, but if you find it interesting or helpful, it's there for you. So also, I penciled in here the laws of thermodynamics. If you've forgotten them, it's not a bad idea to know them. That the first one is the law of conservation of energy. It can't be created or destroyed. Then entropy always increases in a spontaneous process. And this one isn't really pertinent. The last one, and I guess it's always pertinent, but we don't talk about it a lot. And that is the only time entropy is zero is at 0 degrees Kelvin, or sorry, there's no degrees Kelvin, 0 Kelvin, which is a theoretical temperature anyway. But anyhow, let's move on from there. So this is that table, 6.2. I don't test my students on this. I think the bottom line is that you just know if, as you have, what is it? I said a change in delta G of about 6 kilojoules per mole. It gives you about 10 times or a tenfold change in the equilibrium constant. It's nothing more than that. Anyhow, so if you're wondering, okay, this is all well and good. I think I'm part of the way with you on delta G, delta H, delta S, K equilibria. Yeah, I think I understand most of this. What kind of question would you ask me about this? Well, let's take a look, okay? So these are the types of questions that I would expect you to be able to answer. And you'll see that some of them are pretty straightforward. Some of them take a little bit of thought. But let's take a look at the first one. It says, in each case, use the data to determine whether the reaction favors reactants or products. So in A, I'll just ask you guys, if you have some reaction and you calculate the delta G and it turns out that it's positive 1.52 kilojoules per mole, is that going to favor reactants or products? Anybody? It's not a trick. It's exactly, thanks you guys. It's going to be reactants, right? Reactants. Because in order for it to favor products, the delta G has to be negative. Good. What about the next one? If you have a delta G, or sorry, a K equilibrium that is less than 1, it's 0.5, is that going to be mostly reactants or products? Yep, it's going to be reactants again. There we go. So reactants again. Only have crummy reactions here. Okay, let's try C. In C, it says a reaction carried out at 298 Kelvin. Your delta H is 33 kilojoules per mole. And then your delta S is 150 joules per mole. Notice that the units don't match up here. They did that on purpose. It's kilojoules and joules. So what I'll do is I'll convert the kilojoules to joules. You guys are aware that 1,000 joules is equal to 1 kilojoule, like that. So I'll just put plus 33,000 joules per mole. And so what we'll do for C is we'll just calculate the delta G of the reaction, which is equal to delta H minus T delta S. So we've got positive 33,000 joules per mole, subtract 298 Kelvin. Can make that prettier. 298 Kelvin multiplied by, what was it? Positive 150 joules per mole Kelvin, like that. So I've gone ahead and done the math already. So here you see that Kelvin cancels out. So I did the math and then I converted it to, so you get negative 11,700 joules. So you get negative 11,700 joules per mole, which is the same thing as negative 11.7 kilojoules per mole. Okay, like that. So yeah, would that favor the products or the reactants? Anybody? If your delta G is a big negative number, it's going to be mostly products. So we'll scribble that out here. Products. I'm going to do D on top because I'm going to run into space here. Exothermic reaction with a positive value for delta S. So look, here's our formula. Delta G is equal to delta H minus T delta S. So let's see here. It says here an exothermic reaction. If I have an exothermic reaction, it means my delta H is a negative number. So I'll just put negative in brackets, okay? Then I subtract my T delta S. T is in Kelvin, so it's always a positive number. And then a positive value for my delta S. So positive times a positive gives you a positive. So if you take a negative and you subtract a positive, okay, you take a negative and you subtract a positive, like that. So what do I end up with? If you take negative 2 and you subtract 2, you get negative 4. So you always get a negative number. So what's the answer? Is this is always going to favor the products. Okay, it's always going to be a spontaneous reaction. And let's try the last one. So E, I'll do it down here on the bottom. It says endothermic reaction with negative value of delta S. So we get delta G is equal to delta H minus T delta S. So endothermic means we have a positive delta H. T is always positive. Then a negative value here. So negative times a positive gives me a negative. So if I take a positive and I subtract a negative, I always get a positive number. And so it's going to favor the reactants. And there you have it, my friends. Everybody with me on those? Any questions about those? Give me a thumbs up if you're with me on those. Yes? Okay, couple. Good. Okay. So that's kind of, what you're expected to know about equilibria. All right. There you go. So make sure you memorize the formula if you don't remember it already. Delta G is equal to delta H minus T delta S. Very important formula. All right. Let's move on from there and let's talk about kinetics. You guys, who remembers kinetics? Kinetics refers to the rate of the reaction. Okay, rate, which speed is a type of rate, right? There's many different types of rates. Okay, but you could say speed is a rate, like the amount of miles per hour, right? It's a distance per unit time. So you can think about the rate of the reaction as being the fastness or the speed of the reaction. So are you ready for this? Okay. What did we just cover for the past, 40 minutes? I said, if your delta G is negative, your reaction is spontaneous, okay? Give me a thumbs up if you're with me on what I just highlighted in yellow. If delta G is negative, the reaction will occur. Cool, okay. So if you haven't thought about this, maybe go take a hike up in the mountains or something and ponder this for a minute. Just because the reaction is spontaneous, the sign of delta G being negative is great. Okay, when I see a negative delta G, I'm like, woohoo, this reaction is going to work. But it doesn't tell you diddly squat about how fast the reaction is going to occur. I hope that makes sense. So let's say you're working in a lab, you want to do this new reaction. You're like, I'm a scientist and I'm brilliant and I'm going to do this reaction. And I calculated the delta G and it's negative and this looks good and this is going to be a new drug that's going to cure a disease. Let's do it, But then you find that the reaction takes 60,000 years. You're like, oh, well, that's not very useful to me. Okay. So again, that's true. That's true. Okay. Just because the reaction has a negative delta G, it doesn't tell you anything about the rate, how fast the reaction is going to occur. And yes, some reactions that are spontaneous are fast. Okay. There's some of them that are super fast, like an explosion, right? If you fire a gun, okay, when the spark from the primer lights the gunpowder, yes, it's very, very fast. I admit that. However, there are spontaneous reactions like this one. Carbon diamond, so diamond is just an allotrope of carbon, like your diamond earrings or your diamonds in your necklace. So graphite is also another allotrope of carbon, which is found in your pencil, okay? The reaction of carbon going from a diamond to graphite is spontaneous. It's got a negative delta G, so you might look at that and be like, oh no, all my diamonds are going to be converted into useless pencil graphite. Sure, it will happen, but it takes millions of years. So again, give me a thumbs up if you now follow me and you're like I did before, but whatever, that just because delta G is negative doesn't mean the reaction is fast. Okay, it might be slow. Okay, it doesn't tell us anything about the speed. So some reactions are fast, others are slow. And us as chemists, I mean, my life, I don't know about you, but I don't plan on being on this earth for like thousands or millions of years. It might be fun, but anyhow, probably not. But anyhow, so the reactions, we have to take time into consideration is what I'm getting at. Rate is important for us as human beings, okay? So let's talk about reaction rate. And what's cool about this teaching kinetics as a chemistry teacher is it's something I always enjoy teaching because I find it's relatively intuitive for students. Students usually don't struggle with the factors that affect reaction rate, okay? So this should be reviewed, all this stuff here. So it says reaction rate is a function of the number of molecular collisions, right? In order for a reaction to occur, you have to have molecular collisions. Molecules have to run into each other. So you have to have a certain number of collisions over a certain period of time. And what's going to affect those collisions? Well, these are the factors: concentration of reactants, activation energy, the temperature, geometry, and sterics. This is one that we're going to look at more in this class than you've ever seen before. and then the presence of a catalyst. The other 4 are things that you would have covered in dirty detail. So do you guys remember this? Who remembers this chestnut? Rate is equal to the rate constant multiplied by the concentration of the reactants. And it's usually reported to some exponent, okay, like N, and then you had to determined experimentally. That's the only way you can get that exponent. You can't just measure it directly. Anyhow, so this number here, we call this the reaction order. Reaction order. Who remembers studying 0 order, 1st order, and 2nd order reactions in general chemistry too? Right? You would have looked at 0 order, and then you would have looked at the integrated rate laws and all that stuff. Okay, so the bottom line is, if you just look at this formula and take it at face value, at face value, you'd say rate is proportional to concentration, right? The higher this number is, the higher this number is, right? So as concentration goes up, reaction rate should go up, right? You see that it's basically written down here. It's true, okay? But the degree to which the concentration of your reactants affect rate is going to be related to the reaction order, okay? So this number here, so this is the reaction order, okay? And again, if you're a UCCS student, this would have been covered in chemistry 1411. You would have seen this in dirty detail in this class. So the order of reaction is represented by X and Y. If you have no exponent, then it's a 1. Okay, it's just taken for granted that it's a 1. So we'd say that this reaction here is a 1st order reaction. You'd say that this reaction here is 1st order with respect to A, 1st order with respect to B, so 2nd order overall, right? So 1 plus 1 gives you 2. And then the last one, you say that it's 2nd order with respect to A, 1st order with respect to B. You add 2 plus 1, what do you get? 3. So you'd say 3rd order overall. Give me a thumbs up if you remember that, even a little bit. Even if you're like, it's a distant memory in my mind, Mr. Dion, okay? I kind of remember that. Yeah. So you're going to have to read the section on kinetics. It's a good idea to do that. But if we think about this, right, let's say if you have the rate, let's say your K is 1, and then your A, your concentration is 1, then your rate would equal 1. But what if you were to double your concentration? Well, then your rate would double, right? You'd have 1 times 2, which gives you 2, okay? If you were to try the same thing over here, let's say your K was 1, we'll just make up a number, and A was 1 squared times 1. Well, that would give you a rate of 1. But then if you doubled A, right, if you doubled A, right, you'd get 1 times 2 squared, which is 4, times 1, which is 4. So you'd get a quadrupling of your rate, okay? So the general idea is that if you have a big K, for your rate law, big rate constant means it's going to be a fast reaction. And if you have a small K, it's going to be a slow reaction, generally speaking, okay? So let's talk about activation energy. Let me say one more thing about the concentration. Can I just add one more thing about the concentration? If you've had me as an instructor before in general chemistry, you would have heard me say this because I say it every time. But I want to say one more thing before we move on. Talking about concentration of your reactants, and I said if the concentration goes up, the rate goes up. One way that it was explained to me when I was a student, and it was funny, and I never forgot it, and I thought it was an easy way to remember it. If you took a room, right? Let's say you took a chemistry classroom, okay? Here's your classroom, and you have a certain number of students in the classroom, and you ask the students, okay, everybody close your eyes and walk around the room. Are there going to be collisions between the students? Yes, absolutely. Okay, but let's say I invited a whole bunch more students, so I increased the concentration of students. Okay, about double or triple the concentration. Now I tell everybody, close your eyes and walk around. Are there going to be more collisions? Yes. So if there's more collisions, that means the rate is going to increase. Anyhow, I hope you find that, slightly useful, okay? So moving on from concentration, what about activation energy? If you don't remember activation energy, you should, okay? Activation energy is kind of that energy barrier that you have to overcome to get from the reactants to the product. So we see our activation energy labeled on this reaction coordinate diagram over here. And the bottom line is that the higher your activation energy is, so if it's higher, okay, it means your reaction is going to be slower, right? Because it takes like less molecules are going to have enough energy to overcome this barrier. So the activation energy, if you don't remember what it is, it's that barrier. It's the minimum amount of energy that you have to have for the collision to result in a reaction. So just because two atoms or molecules collide, that doesn't necessarily mean there's going to be a reaction. They have to not only collide, but they've got to collide with, like, let's say they collide and it's like, we have only this much energy, or we'll only get up to here. No, they've got to collide with enough energy to get over the hump, right? To get over that activation energy. And so that's what activation energy is. And if you look at the distribution of the number of molecules and their energy, and this is at, constant temperature, right? We have a huge distribution of energies, but let's say the activation energy is down here. You can see we only have a certain percentage of atoms or molecules that have that necessary activation energy. So what would happen if we increase the temperature? If you increase the temperature, what's going to happen is the distribution is going to go like this. So then you're going to have more atoms or molecules that have enough energy to get over that minimum energy barrier, that activation energy. So the bottom line is, the lower the activation energy is, the faster the reaction rate is going to be. The higher the activation energy, the slower the reaction rate. Nothing more than that. All right. So what about temperature? Well, this is what I just showed you. You see the curve in blue is the distribution of molecules at a lower temperature, but then as you jack up the heat, the curve moves to the right, and then you have a larger percentage of molecules that have that necessary energy to get over that activation energy barrier. Now, what about sterics? This is something that we're going to cover in more detail in chapter 7. So I'm not going to stress about this a ton right now. Son of a gun, I didn't mean to do that. This is going to be covered in detail in chapter 7, but just follow along with me on the slide. What it says here is this: steric hindrance in the geometry of a molecule or a compound is actually going to have effect on the rate of reaction. So when two molecules collide, they have to collide in the correct orientation. Okay, so they can't just collide any old way. They actually have to collide in a certain way at a certain orientation in order for the bonds to be broken and to be made. So the relative conformation, or the geometry, or the sterics of the compound is actually going to have an effect on the reaction, because if the reactive conformation of a compound is high energy, it's going to spend less time in that conformation. And so the probability of a collision is going to be, that results in a reaction, is going to be low. But if it spends a lot of time in that reactive conformation, then there's going to be more effective collisions. And so your reaction rate is going to be high or fast. Okay. Now, again, this is going to be covered in a lot of detail in chapter 7. So we're not skipping it, but we'll get, if you're like, I need more background, trust me, chapter 7 is going to give you all the background you need about primary alkyl halides and tertiary and that, okay, that idea. The next one is a catalyst. I usually go over this pretty quickly because my students don't struggle with this, I find. A catalyst just speeds up a reaction rate by lowering the activation energy. And not only does it lower the activation energy, it also oftentimes provides an alternate pathway. So an alternate and faster pathway, but it just goes a different route, okay? So you see that the uncatalyzed reaction follows this pathway, but with the catalyst, it actually reacts a little bit differently. You see it's got all these transition states in here. But the bottom line is that the lower the activation energy, which a catalyst does, faster reaction, okay? Nothing more than that. So when we're reading energy diagrams, okay, and these are both reaction coordinate diagrams here, okay? You've got to, if you didn't separate kinetics and thermodynamics as a general chemistry 1 student, if you weren't able to do it, or you struggled with it or whatever, don't hesitate to ask me any questions about it, because when you leave this class, or even when you just finish chapter 6, I want you to be sure that you understand the difference between kinetics and thermodynamics, and understand that they are not the same thing. So to repeat myself one more time, kinetics is how fast is the reaction going to happen, right? How much time am I looking at here? Am I looking at 5 minutes, 5 hours, or 5 million years? Okay. How long is this reaction going to take? That's kinetics. That's related to things like the activation energy, right? Sterics, concentration. Okay. That's all that stuff that you would have covered. Rate is equal to little k multiplied by the concentration of reactants to some exponent. Okay. That's the speed. Thermodynamics, that's based on like delta G. The delta G, is it negative or is it positive? Okay. How much reactants am I going to have and how much products am I going to have? That's an equilibrium process, right? That's all based on things like K equilibrium. It's something completely different. It's based on the relative energies of the reactants and products. So again, thermodynamics tells us how much of the products are we going to have when this thing's all done, when it reaches equilibrium. And kinetics tells us how fast is the reaction going to go. Okay, so kinetics refers to the rate, whereas thermodynamics refers to equilibrium concentrations, how much reactants and how much products do I have at the end. They're two different concepts. So this is a question I've seen on a final exam. I don't know if it's on your final exam, but this question has been on an ACS final before. This question right here, okay, where it gives you two pathways for A and B. One of them leads you to C and D, and one of them leads you to E and F. If you look at those two, the blue, so we'll call one the blue curve and the one the red curve. Could anybody tell me which one is going to occur faster? Which one is the faster reaction, the blue curve or the red curve? It's not a trick. I think the answer is on the slide. Yeah, it's the blue one, right? The blue reaction is going to be faster. Why? It's going to lower activation energy. If it's got, right, this is the activation energy. The other one's way bigger. So lower activation energy, yeah, it's going to be a faster reaction. So that means that this product, we say it's kinetic product, or we say this is the kinetic pathway, because it's faster. But then in terms of thermodynamics, which products are going to be favored? Is it going to be C or D or E and F? Well, you see that not only is the blue pathway the kinetic pathway, but you see that C and D are the thermodynamic products because they're more stable, right? There's a bigger delta G gap, right? This delta G gap is bigger than this little delta G gap here. So the delta G here for the C and D, the delta G is more negative, okay? And so this is also the thermodynamic product. I'll just put therm product, okay? So sometimes students will think, well, if the reaction's fast, maybe the products won't be stable. No, the blue pathway, not only is it giving you the most stable product, it's a double whammy. It's much better, right? It's faster and it gives you something that's more stable, okay? So the formation of C and D in this case, in this specific case, okay, it's just an example on a slide, are both the kinetically and thermodynamically favored products, products, because it's C and D. So there you go. So now if we look at this coordinate diagram here, you can see that E and F have a lower activation energy. So E and F are kinetically favored, okay? However, if you look at C and D, right, there's a bigger delta G gap. So C and D happen to be thermodynamically favored. So now, hopefully, if you look at this reaction coordinate diagram, this one here, and compare it to this one here, hopefully it gives you a little bit more insight as to why chemists are so hung up on these diagrams. If you've ever wondered, like, why do you always have to show me these graphs? You know, that's why. It's because you can look at it very quickly and say, that's the faster reaction. Oh, that gives you the most stable products, right? Chemists like to do that kind of thing. So when you looked at the alternate pathway for that, catalyzed reaction, remember we had the pathway, so we had the pathway without the catalyst, or let's do an exothermic reaction. We had something without the catalyst, and then we said with the catalyst, right? And it went a different pathway. This is me really, actually that's too many. Son of a gun, Mr. Dion. I'm just excited about the topic. So we said with a catalyst, right? Catalyst gave you, a different pathway. Well, if you're wondering, like, what are all these bumps? Okay, when you see bumps in your reaction coordinate, what it means is this, is at the top, that the maxima, these are called transition states, okay? They don't really, you can't isolate a transition state. It's very fleeting, it's very quick, okay? It's something that kind of passes between as you go from the reactant to products. And the intermediates are kind of like, those can be things like carbocations that occur along the way throughout your reaction. So it says here, this is a better way of defining it. It says transition state is high energy state that the reaction passes through. It's kind of like where the bonds are broken and formed simultaneously. It's kind of like bonds are partially there and partially broken. Transition states, like I said, you can't put one in a bottle and carry it around. They're fleeting, they're very rapid. They cannot be directly observed or isolated. They can be studied, okay, but you can't take a transition state and go for a drive with it or something. So the the transition states are the energy maxima, and they represent where bonds are being broken and formed simultaneously. Whereas an intermediate, these are the energy minima. Intermediates, on the other hand, they are observable. Okay, they are actual chemical species that exist, like you see this carbocation here, for a period of time before they react further. So again, the maxima are the transition states. This is where bonds are being broken and formed. And the minima, those are the intermediates. We can actually observe those for a period of time. And so before we move on to the very last, or before we take our break and get into section 6.7, there's one more thing which I have to cover with you, which is the Hammond postulate, which might seem complicated, but it's actually not that bad. I wouldn't say anything is simple in organic chemistry, but all it is this. You guys remember exothermic and endothermic and exergonic and endergonic reactions, okay? And you know the idea of a transition state. So all the Hammond postulate is this. If you go to your transition state, if you have a reaction that's, let's say, exothermic, right? This is an exothermic reaction here. You see how the energy of the transition state that I have the red circle on is closer in energy to the reactants than the products. All that means is that the transition state is going to look more like reactants than products, okay? So if you have an exothermic process, it means your transition state is going to look more like the reactants because it's closer in energy. And if you have an endothermic reaction, you see the transition state is closer in energy to the products. So that means when you study the transition state, it's just going to more closely resemble the products. That's all it means. There's nothing more than that. And if you're like, that's it, what do I do with that? Well, we're actually not going to do that much with it yet, but we are going to do something with it later on. For now, you just kind of have to know the postulate, okay? In an exothermic reaction, transition state mostly looks like reactants. In an endothermic reaction, the transition state mostly looks like the products, okay? And that's it. That's the 6 sections. So those first 6 sections are kind of, like I said, it's a lot of general chemistry 1 and 2. But as you get into section 6.7, where we talk about nucleophiles and electrophiles, this will be new content for you. So I think this is a good place for us to take a break. And just so you know, the concepts that are covered in 6.7 until the end are concepts that are never going to go away. Okay, I can tell you that we lecture for maybe weeks in in organic chemistry too, where delta G and delta S might not come up, but nucleophiles and electrophiles are going to come up basically in every lecture, pretty much from now until the day you say goodbye to organic chemistry. Okay, all right. So let's take a break. Go. There we go. All right. Sorry I went on so long, but